on to question 4. So the first thing we need to do is complete the following equation for beta minus decay of strontium into an isotope of yttrium. So with beta minus decay, what you need to remember is that a neutron is going to turn into a proton. So the first thing that we need to get these colours right. First thing that we need to do is maybe adjust the proton number. If it's gaining a proton, then the proton number is going to go up by 1, and the top number, because we're not actually adding any nucleons, we're simply changing one neutron into a proton, that will remain the same at 90. Of course, charge is always conserved in these cases, so we've got an extra charge down here, we've got an extra proton charge, so we have to emit an electron as well in order to balance that charge. Electrons don't have any nucleon number and it's a -1 charge. So that's all very well, but this actually upsets lepton conservation, because now we have an electron with a lepton number of -1, and over on this side we have no lepton numbers because there's no leptons involved, so we need to give an anti-lepton which will come out, and in the vast majority of cases that will be the anti-neutrino. In fact, in all cases at A level you can assume that to be the case. Okay, part B. During beta minus decay of a nucleus, both the nucleon composition and the quark composition change. State the change in quark composition. Right, so what you need to do is look up your formula sheet to find out what the charges of quarks are. I'm going to just write this down before I start. So I know that, I'll do it over here. I know that an up particle has a charge of 2/3 and a down has a charge of a -1/3. I'm noticing the strangeness later on, so I'm just going to put that in as well. A strangeness has a charge of -1/3 also. This is the charge of the fundamental particles. In beta decay, we have a neutron, which is an up, down, down, changing to a proton, which is an up, up, down. And that makes sense, because if I look at the charge on this, I've got 2/3 here and 2 lots of a -1/3, so that would be 0. So my neutron here has a 0 charge, which we know. For this one, the proton, we've got 2 up particles, both at a charge of 2/3, and a down particle at a -1/3, so that will give a charge of +1, which of course is the proton. Right, so the change in quark composition, we just need to see which quarks have actually changed. Well, the down quark has changed to an up quark, so we can simply write down has gone to up, and that's all that's happened in beta decay. Right, moving on. A positive kaon consists of an up quark and an anti-strange quark. This kaon decays by the strong and weak interactions into 3 pions. 2 of the pions have quark compositions of up, anti-down. The third pion has a different quark composition. So the first thing, easy, name the unique family of particles to which the kaon and pions belong. These are particle-antiparticle pairs. These are called mesons. They don't exist for very long because they annihilate each other, and they're always a particle and an antiparticle. Next question, a bit harder now. Tick the box corresponding to the charge of the third pion. So let's do an equation and work out what's going on. We've got an up anti-strange has decayed into an up anti-down plus another up anti-down plus a mystery particle, which we don't know. So what I should do is work out the charge for all 3 of these things, and then see if we can compare them and work out what the charge should be, remembering of course that charge is always going to be conserved. So the charge for an up anti-strange, well, an up is 2/3 that we've got over there, so it's 2/3. A strange is a -1/3, I'm missing that wrong, there should be a 1 up there, is a -1/3. So the charge for this is going to be 4/3 plus a -1/3 gives us +1. The charge for the up anti-down particle, that's going to be 2/3, and it's anti-down, so that's going to be plus 1/3, not minus 1/3, because it's this antiparticle, so that will also give us +1, and of course this one is the same. Do note that charges come in integer values only. You're not going to get 2/3 of a charge in a particle. That doesn't really exist in nature. That's why we keep the fundamental unit of charge as 1. We don't split it into 3. And as you can see here, I've now got 2 charges on that side, 2 plus charges. Still got my 1 plus on the other side. So this must have a -1 charge. So my answer is -1, which is, of course, negative. Quite a tough question for 1 mark. Okay, moving on to part 3. Just scrub this out. So parts 3 now. Positive kaons have unusually long lifetimes. Let's get a decent colour. Give a reason why you expect this to be the case. Basically, because they have the strange quark. Anything with strangeness in it is slightly unusual, hence the name. So that will lead to a slightly longer lifetime. Part 4, 1 mark. Name the exchange particles which are involved in the strong and weak interactions of the kaon. You need to know the exchange particles really for all 4 fundamental forces. So the exchange particles that are going on here, the bosons, are the gluons. I believe there's 8 different types, but we don't need to learn all them or do anything. We just need to know that a gluon is an exchange particle for the strong force. The weak interaction, this is a W plus, W0, or W minus boson. The electromagnetic, that's our old friend the photon, no charge. And gravity, haven't got a clue. They think it's called a graviton, but it's not been discovered yet. You won't be asked really about that. It's still a very modern area of physics. So, of course, what do we need? We want the strong interaction, we want gluons, and we want the W plus, W0, or W minus boson. Or, in fact, a Z0 you can have in there as well, I think they're called.